Hi, I am Kinsani Maimane, and I will be going over the convective heat transfer that occurs inside a gearbox casing. The gearbox casing simulation indicates the temperature variation that the casing experiences. The inner walls of the casing experience the highest temperature, which is 415 Kelvin. And this is due to the heat generated by the gears, which is then dissipated into the oil and air. However, in this instance, it is assumed that the casing is filled with oil only. It's important to note that the heat transfer between the lubricating oil and the inner walls is that of forced convection due to the laminar sublayer. Assumptions and boundary conditions for the simulation is that heat generated by gears is at the center of the gearbox, and that the heat generated inside is transferred directly to the inner walls. This is why the temperatures yielded by the simulation would be much higher than those expected of a theoretical and analytical solution. And once again, this is due to the fact that the simulation assumes that the casing is filled with oil only. Another assumption made is that the geometry of the inner walls is that of flat plates. It's important to note all these assumptions and simplifications when analyzing the structure. Another assumption is that the steady state analysis. Finally, it is seen from figure 3 and 4 that the heat transfer from the oil to the inner casing decreases as you move from the center of the casing outward. This is also seen with the temperature variation, which goes from the highest to the lowest, which is 415 Kelvin to 363 Kelvin. Figure 3 also shows that an increase in gear speed will increase the heat coefficient of oil. And this is due to the fact that the heat coefficient of the gears is the same as that of the oil. This was an interesting assignment, and I learned a lot about simulation, particularly the importance of it when it comes to designing, as you're able to identify critical areas in a structure, and this allows you to redesign it and improve it. Overall, this was a great learning experience. However, it would be beneficial for students to perhaps gain more experience in this software and also understanding how to use that with analytical data. The option of choosing your own topic is also great, as it allows us an opportunity to expand on what we might be interested in. For me, I learned a lot about the gearbox and particularly how broad it is and complex it is when you involve gears. Thank you.
My name is Mitham Somi, and I'll be doing results and discussion for conductive heat transfer part of this project. This is just a temperature profile overview that was obtained from the simulation. The minimum temperature obtained was 304 Kelvin and 415 Kelvin. The cross-section of the gearbox is also displayed here so that the temperature variation can be clearly seen. When we are focusing on the thickness of the casing, our temperature distribution started from 304 to 356 Kelvin. The analytical results also depicted the same temperature profile. The line of best fits that was obtained was a straight line because there's nothing generating heat within the thickness of the casing. However, when we explicitly look at, inside the cavity of the casing, The arc obtained, or the line of best fit obtained, was parabolic, and this was due to the heat generated by the gears that was transferred to the oil and to the casing walls. The minimum temperature inside the casing was 356 Kelvin, and the maximum was 415 Kelvin. In this assignment, I learned that SimScale is a very accurate and convenient tool since it minimizes error. The overall experience was very interesting because we got a chance to compare results obtained from empirical equations and the simulated results. The application of theory to simulate a very complex engineering problem was very, very interesting. The only problem I had with SimScale was the post-processing time, which delayed results, but this was a very, very, very minimal problem. In future, students can have a preview of how the SimScale tool work so that they can just familiarize themselves with SimScale. The idea that you have students having to propose problems is very interesting, and this idea should not be neglected in future because it gives students an idea to do research and try to solve complex engineering problems. Thank you.
Greetings. My name is Titus Ramusola, student number 1424385. Today I'll be explaining the process of generating heat transfer simulation for our transmission casing. The first step is to prepare the Cad model in Inventor, but before you can do that, you need to have a clear understanding of the physical problem. This will help you to do a cleanup work on your geometry. In this case, we do not include any mounting features or holes for bolts because they do not have a significant effect on the results. Now, reducing such geometry complexities will help you to obtain more accurate results in a short period of time. Okay, the second step is to import your geometry in SimScale environment, set topological entities, entity sets. And now this is just to put restrictives to our model and also to describe how our elements are bounded and connected. Now we do this for efficient and accurate setup of the simulation. Now the third step is to click on simulation. Heat transfer tree will pop up, and also with branches. The first thing is to set up our material, choose our material and also the material properties. We need to assign boundary condition. Now our initial boundary condition will help us reach convergence solution faster, saving us computational resources. For this model, we assign 3 boundary conditions. The fourth thing to do is the third thing to do is to choose the format of your results. If you want your results in temperatures or heat flux, you have to assign it here. And then lastly, you need to do your mesh, to define your mesh. So our mesh refines our results. Here you can decide on the trade-off between the fineness of the mesh, which is the accuracy of your results, and the required computational time. And lastly, you need to run your simulation. The results are as follows. As you can see from the inner walls, heat transfer is prominent. And we can see the maximum temperature reaches 415.591 Kelvin, which is similar to the analytical solution. We can also see that there's a heat distribution over the surface of the thickness of the casing. Now, in conclusion, what I found difficult about this is actually cleaning up my geometry. And what I found, what I enjoyed about the assignment is you can actually get to see your temperature distribution as compared to having diagrams, right? And then the lesson learned here is that communication is key in every group work.
Greetings. My name is Thandazani Nkosi. My student number is 11-399-77. I'm here to give a brief summary of what I've done in the project in the assessment for heat transfer. So our group was analyzing the gear casing. We wanted to see how the temperature varies along the walls of the casing. So for the simulation part, we first had to create a drawing in Autodesk Inventor. Then we imported the drawing to SimScale. This was our drawing. From here, we selected the topological entities to determine our different heated regions. After that, we set up the boundary conditions. The heat flux conditions, we got them from our group mates who were doing the analysis. Then we selected our material that we're going to use. We chose to use iron. Also, we can change the fineness of the grains. Then we ran the simulation, and these are the results that we got. We saw how temperature varies along the walls of the casing. What I've learned is how to perform heat transfer analysis using SimScale. I did have a bit of fun, although there were challenges, because we couldn't simulate a closed casing, so we had to open our casing in order to be able to select the inner surfaces to set up our boundary conditions. What we can do to improve our results is to decrease the assumptions that we have. And no, I do not have any random dots. This is what I've done. Thank you.
So from the imported component that we want to like simulate and see the results, like visual representation of the results based on the different sort of boundary conditions set. This is the mesh that we generated, and so for the results, it comes out as something like this. So after sectioning the results, after cutting the plane on the x-axis, this is how the temperature distribution can basically be seen, ranging from inside from the casing when it's very hot. Assumption is that after it immediately just stopped going outside when it's getting to it's the atmospheric temperature. So yeah, the temperature distribution can clearly be seen here. It does look a bit linear. It can be assumed to be linear basically, and yes, and then the results are how they came out, and then the mesh generated sort of surface on this side can clearly be seen like this, and the temperature distribution again can also be seen ranging from inside the casing going all the way out. Yes, and also on the other side, temperature distribution from inside going all the way out, and how the entire casing is basically affected by the temperature basically. So yeah, the one that we used was this one because it does show not all the sides of like and inside the casing show we're going to get the same temperature because of the gear locations and everything. So this is the one that we use because it demonstrates the precisely what we wanted to demonstrate, especially what is happening within inside the temperature casing. So yes, and then what I basically learned from this was that you can use the thermal sim scale for not only like thermal simulation, but also for other types of simulation, from fluid simulations to yes, from thermal simulations, fluid simulations. Every time you can, and I did enjoy using the simulator, and I wish I could actually spend more time simulating. However, I cannot because I need to study other subjects. However, I will definitely personally use this in the future, as it made my life easier. Yes.